So in previous videos, we've largely concentrated on one behavior at a time, the way a particular contingency, a specific schedule of reinforcement, might affect the probability or the rate of this one behavior we're observing. But in real life, if the probability of one behavior goes down, it kind of makes sense that some other behaviors might become more probable. If someone's shocking me every time I eat a cheeseburger, yeah, I'll become less likely to eat cheeseburgers, but in turn, that'll make me more likely to eat other things. If a teacher in class consistently rewards a child only when she raises her hand and waits to be called on, then that behavior will become more common, but other behaviors like blurting out the answer will become less common. What I'm saying is, in any given moment, in any given scenario, we have a choice of lots of different behaviors. So the question is, what determines which choice we make? What determines which behavior or behaviors we end up doing? That's what these next few videos will be about. Now, when we study choice in behavior analysis, we might operationalize it as something like the distribution of operant responses among alternatives, meaning among alternative sources of reinforcement. Basically, how much you do each of the possible behaviors when some of them pay off differently than others. And sometimes we might also talk about a preference someone has. For an individual to have a preference, we're just saying one option is chosen more than the others. Like, if you're at a casino and can choose between two slot machines, one of which is paying off a lot and one of which is barely ever paying off, you'll eventually develop a preference for the one that pays off a lot. And your operant responses, your behavior, will be distributed heavily on that machine and less on the other. Now, as usual, if we want to understand the basic mechanisms of behavior, we start by testing it in its simplest form in a nice controlled laboratory environment. So one way we might study this is by kind of just setting up two slot machine-like levers in an operant chamber, each with their own schedule of reinforcement, and we see how different setups there affect choice behavior, affect preferences of an individual, kind of see what controls they're choosing. So we call this using concurrent schedules. Rather than a single lever that's on a particular schedule, now we're talking about two different levers in the operant chamber, or two different buttons that the pigeon can press, or two different options that the human can work on, two different like machines the human can work on, or whatever it is. But what we call concurrent schedules is just giving two or more, it could be more, but you know, the simplest form we'll think of giving two options, two buttons, two levers, something like that, each with its own schedule of reinforcement. So they could be reinforcing at a different rate. Now in the lab, we might use a discriminative stimulus, an SD, right, for each option, and that might be something like a different light, just to signal like, oh, this is this option, this is that option. Like a blue light over on the left lever and a green light over, above the right lever, something like that. Now initially, obviously, if you're throwing a random ass rat in there, it's not going to know what blue or green means, right? It means nothing at that point. So they don't know at the start which schedule is better. They might just kind of try both of them. Meanwhile, the dependent variable that we'll be measuring is how much they choose each option or how much time they spend on each option. Like, if you put the blue light and its lever on the far side of the operant box from the green light and its lever on the opposite side, they kind of have to go to one side or the other to use the lever and sit there working on it for a while trying to get their treat. Now, regardless, once the individual has been in this chamber doing this setup for a while, once they've had access to both options for a long time, they've gotten plenty of experience with both, eventually what we see is they settle into a steady state of behavior, kind of a consistent pattern of how they respond when given this particular choice. And it's usually pretty much the same. You throw all rats or all pigeons in the operant chamber, and they'll basically respond in a pretty much the same way. If one of the levers is consistently better than the other, they'll end up on that lever, something like that. So let's think about what this might look like with a rat in a lab, in an operant chamber. So imagine with this adorable little rat here, we offer two options. So the choice is just which of these two levers should I use? So the option might be between a lever on an FR10 schedule and one on an FR20 schedule. So think for a moment, you might pause the video if you don't remember and think through like what is an FR10 schedule, what's an FR20 schedule, which is better. So both of these, they give the same treat, but in this case, one of them only takes 10 lever presses. The other takes 20, like twice as much work for the same payoff. So what do you expect to happen? What do you expect this rat's behavior to be? Well, clearly the rat will just end up spending all his time on the yellow option, right? So comparing a couple of fixed ratio schedules, it's kind of not very interesting. Like, obviously they're just going to spend all their time on the one that's better. And the other is just always worse, and they'll end up never spending any time on it. So that's not a great way to test choice behavior, using fixed ratio schedules like that. What about if we used variable ratio choices, like VR schedules? So now we give, let's say, a blue option that's variable ratio 90, and a purple option that's VR 25, meaning on average around 25 lever presses to get that treat versus around 90 or so on average for the blue side. What's the rat going to do? Again, after it has a while to play around with both these levers to figure it out, after it's been doing this for days, where is it going to end up spending its time or spending its behavior? Again, this one's probably pretty obvious, right? After some experience, the rat will clearly spend all of its time on purple because that maximizes the payout. Basically, if we study a simple choice situation like this where we're just comparing ratio schedules, whether FR or VR, one is clearly going to be better. Ratio schedules, then they basically always lead to exclusive preference for the better schedule. Like if you're offered the exact same job at some place that's identical in all other ways, so it's the exact same job, every variable is identical, but one of them just pays a higher rate of pay, right? A higher wage. You're probably just going to spend all your time picking up shifts at that place and not at the other place. So that's a downside of using ratio schedules to try and study something like choice behavior in the laboratory. Like, yeah, it is accurate, but it's not very interesting. So this doesn't help us understand the subtleties of choice behavior. We shouldn't use schedules like FR or VR. So forget ratio schedules then. What if we set up a concurrent schedule, so two choices, but with fixed interval setups, fixed interval schedules of reinforcement? So like the red option here might be set to a fixed interval 5-minute schedule, meaning if you get a reinforcer off there, you pull the lever, you get a reinforcer, there's a 5-minute delay, exactly 5 minutes before that lever works again. And then the orange might be set up with like an FI 30-second schedule. So that one you have less of a delay, less of a fixed interval of waiting before you can pull the lever and get a treat again. So what do you think the rat's steady state behavior will eventually look like? Like once it's tried both of these out a bunch, has a bunch of experience, what is its behavior going to end up looking like? You might actually take a minute to pause the video and try and predict his behavior before moving on. Okay, well, we know the orange one pays off a lot more than the red one. So you might think he'd just end up hanging out at the orange side all day, right? Because it has less of a weight. But that's got a downside. If he just hung out at the orange one, he would be passing up extra treats he could be getting from that red side once in a while. So actually what we find is the rat will spend some time on both sides and just more of his time or more of his behavior on the orange side. It's obviously not conscious or not in language like this, but the little quote I put here is just to kind of pump your intuition. You might imagine the rat kind of trying to figure out the perfect plan, or his little, predictive little brain trying to figure out the perfect plan to maximize his payoff. And what he's going to settle on is probably something like hitting orange every 30 seconds or so for about 5 minutes, and then briefly bounce over to the red for a treat, then go back to orange and hit it, every 30 seconds or so. That way he's not wasting the treats on the red side. So now let's try another example. Let's do FI 1 minute on the black side and an FI 1 hour on the white side. So same basic idea, but just to make sure it clicks here. After he gets enough experience figuring out these timings, what will his steady state choice behavior look like for this little rat? So you might pause the video and try and predict it. Well, the black side is clearly the best place to be most of the time, right? Because you can pull the lever for a treat once every minute. But occasionally white works too. So what we see is the individual will mostly stay on the black side for an hour, but then switch to the white side once each hour, once in a while, before going back to black again. So anytime we set up a choice like this between fixed interval schedules, they eventually figure out exactly when to switch at regular periods, right? Or at least, I say exact, but I mean roughly, because they don't have, a clock to look at exactly or anything. But they figure out kind of the ideal times to switch at pretty regular periods because it's so predictable. The problem is it's probably too predictable to model a lot of real life choices that we'd find interesting to study when we're studying choice behavior. It also leads to a problem, kind of a side effect. Once they're in that pattern of mostly sticking to one side and just occasionally sampling the other side, that means they're not going to be very sensitive to changes in the rate of reinforcement or the relative rate of reinforcement between the two, because they're not sampling the other side enough. Like if we change that white schedule, it's harder for them to notice and adapt to their behavior. So again, this isn't the best way to study these things. Now, that doesn't mean what the rats are doing isn't genuine choice. Like they are making a choice. And the data we get in these scenarios is still accurate when we use FR or VR or FI schedules, but it's not very interesting because we're studying choices that are so obvious and so easy. So it's kind of just clear what the best behavior is, and they end up doing that. Whether you throw a rat in the cage for a long time or a pigeon in the cage for a long time, doing these things over and over, like they just end up figuring out the best behavior and doing that, and it's all the same. So it's not very scientifically interesting, right? But we can study harder choices using this concurrent schedule setup, this little 2-lever or 2-button setup. So let's imagine, instead of the other options we've talked about, let's say we set up something like a VI 30-second schedule and a VI 35-second schedule. Now remember, this is basically saying that on average, the gray lever will be turned off for around 30-ish seconds before it'll pay out again. But sometimes longer and sometimes way shorter, right? Likewise, on the red side, it'll pay out again after roughly 35 or so seconds on average, but sometimes it pays off again immediately, and sometimes the wait is really long. Now, imagine we've got this rat, right? This rat in the box who's experiencing both of these schedules. He's trying both of these levers for a long time, gets lots of experience. He's trying to maximize his payoff. The question is, what will his steady state behavior end up looking like once he's been in this setup for a long time? By the way, before you start thinking this will only apply to rats, we've done lots of studies with this exact same design, this exact same choice setup, but having college students come into a lab and choose between two levers that pay out actual money they get to take home. So instead of imagining a rat, just imagine you're a college student and these levers on opposite sides of a room will pay out a dollar bill every 30 or so seconds on average. And maybe the other lever pays out a dollar bill every 35 or so seconds on average. And the question is, if you really want this money, if you're desperate for this money, let's say you're a poor college student, what will your behavior eventually look like? If you wanted to truly maximize how much money you leave the lab with, or imagine every time you pull that lever, like when it pays off, it's paying off a $20 bill or a $100 bill, and you only get to play this game for an hour. You want to leave with as much money as possible. The question is, what's the ideal strategy? If you had enough time to practice this a whole bunch, what strategy would you settle on to maximize how much money you leave these two levers with? Or what will the rat eventually do to maximize its treats? So you might pause the video a minute and even maybe on scratch paper try and sketch this out. Just think about, try some alternative ideas and see what would be the ideal way to split your time. So this one it's harder than it initially looks. And that's because the gray one certainly pays off more often. On average, the gray one will give you more payment on average. So you might be tempted to spend all your time working on the gray lever, but that sucks because the red one also pays off pretty well too. So if you ignore the red side, you're wasting tons of potential payout. So your best bet is actually to work both of them sometimes, to do some behavior on each, kind of switching sides now and then. If you do that, you'll end up spending a bit more time on gray, yeah, but not being exclusive to gray. And that is mathematically the best way to maximize your payoff. And indeed, it's what rats end up doing, what pigeons end up doing, what dogs end up doing in this setup, and even what undergraduate college students end up doing in this same kind of scenario. And this allows us to test some interesting things about how behavior is controlled by the choices in our environment. In other words, how the choices we make or the preferences we end up with are determined by things like the schedules of reinforcement that are offered to us by our environment. So VI schedules They're the most commonly used to study choice behavior in the lab, like by behavior analysts. It's nice since individuals don't exclusively choose one side, right? Because it pays off to do both sides, at least sometimes. And the fact that they're sampling both sides kind of fairly regularly means that with VI schedules, they're sensitive to the rate of reinforcement on each option. And if things change, they can learn and they can adjust their behavior to those changes in reinforcement. So we can study that as well. Basically, in this kind of setup, the reinforcer is less predictable with VI schedules, so they frequently sample both schedules to learn them. Now, that's the main thing I want to talk about in this video, but I'm going to mention one little side note at the end here. Just for a sort of methodological side note for concurrent schedules. There's a slight problem that can show up as a side effect with concurrent VI schedules when we're studying choice behavior, and that's like what might happen sometimes with one of our subjects is he just ends up constantly going back and forth. Like he's literally just bouncing across the operant chamber, press the gray lever, press the red, press the gray lever, press the red, press the gray lever, press the red, back and forth, switching on every single response. That sometimes can happen. It's not with all the creatures, but sometimes when we put them in the setup, they end up in a pattern like that instead of the expected steady state pattern that we would expect. Now, that's not the ideal behavior to maximize his rewards, right? Going back and forth like that isn't going to be perfect. Though, of course, it works okay. Like, it works enough that he's still getting a good number of treats. Like, it's not the perfect strategy, but, good enough, right? But he kind of gets trapped in this pattern of constantly bouncing back and forth, and then his poor little brain never pieces together the difference between the two sides, and thus can never piece together the better strategy to get more treats. So he ends up spending 50% of his behavior on both sides, even though the schedules are a little different. One is better, and he probably should spend a little more time over there. So the little dude gets stuck in kind of a subpar rut. What is it that might have caused this little guy to become so obsessed with switching sides constantly that he won't be able to learn the relative value of each side? Well, think of it this way. Early on in the learning, when he's just starting to play around with the levers, when he switched from hanging out on one side to hanging out on the other side, he might happen to have gotten reinforced right after moving over to the other side. Like the first lever pull, he moves over there, presses the lever, and it works. Just assuming that side's timer happened to be up. So if that happens, the rat's brain might not realize anything about the unpredictable VI timing, and instead its brain just noticed that the behavior of switching sides, the behavior of going to the other side, had happened right before the lever pull gave a treat. In other words, the behavior of switching levers might be what's reinforced when the treat comes out, rather than the behavior of pressing lever A, right? So they start to think switching is what gets them the food, rather than thinking each of these levers give me food at different rates. So they don't pay attention to one button or the other. They never end up learning about the schedules. They can't compare them, and thus they will never maximize their payout. They just get stuck in a loop because they initially got tricked by a coincidence into thinking that the whole setup just rewards them for side switching behavior. Now again, this is just a random little side effect we can sometimes run into, but it can muck up our data, right? When we're trying to study choice behavior with VI schedules like this. Thankfully, there is a really easy fix we can add to our setup to avoid that coincidence where the switching itself seems to be rewarded for their little brain. So what's the solution? We add something called a changeover delay. Basically, you add in a brief little delay where switching sides won't ever instantly pay off. So kind of going over to the other side, trying the other lever, it won't immediately work, even if the timer was up, even if the VI timer was up and the lever should be working again. We've added a little bit of a delay when they do the changing over to the new side, so that the lever won't instantly work, even if the 35 or whatever seconds was up on the red one. So you have to wait at least a tiny bit of extra time when you switch. After that brief little changeover delay is done, then whether the red lever is working, right? It just depends on whether its normal countdown timer was up, like whether those 35-ish or so seconds had passed. So in other words, if there's like a 5-second penalty for switching behavior, they won't switch sides non-stop every 2 seconds. There's no more of that confused loop of superstitious behavior due to some early coincidence. So the changeover delay, it fixed that. Now we can actually see how the rat, or rather how its predictive little brain, will eventually piece together the relative payoff of the two sides and make its choice between them, eventually reaching a steady state to maximize its payout. So this is just a methodological quirk, something that helps us avoid that stereotypical, or that kind of, stereotyped behavior. But the main idea here that I wanted to get is just that idea of concurrent schedules. So that's enough to give you the basic methodology we might use to study choice behavior in a really controlled way in the laboratory, to just really get at the fundamentals of what determines our choices. So we use 2 or more concurrent VI schedules. There could be 3 levers or 4 buttons or something like that, right? And we see how differences in those schedules predictably cause certain choices in an individual. With that kind of information, we can explain why people choose to do what they do, and we can even use that understanding to make people prefer what we want them to prefer. But that means we've got to use this tool of concurrent VI schedules to really get a deeper understanding of choice behavior. So that'll be the next video.